So I want to pretty much finish off chapter 1 today, and then on Wednesday, if there are questions going back over chapter 1, we can take a little bit of time to go over those. You can always come to my office hours and ask questions also. But the end is in sight for chapter 1. We only have 2 more things really to end up discussing here. And again, we lay out these ideas in chapter 1. We'll spend chapters 2, 3, 4, and 5, and 6 sort of putting some structure, making sense out of those things. Okay. So the in 1.5, right, there is something called Bayes' rule. And I gave you an example of Bayes' rule on Friday at the end of class, the last calculation we did. And then did anyone not get an email over the weekend? I think everyone's on Blackboard. I just want to double check because I send, especially for this class, I sent a lot out. And then this has gotten easy now that we use cameras so often. People ask questions and I can type a big long email. It's actually quicker for me just to, put a video together and do it. And so anyway, so I sent out an example of Bayes' theorem and an example of the law of total probability. Both of which we'll see here in this example. But anyway, so I sent a video. If you want to see even an additional example, you can go ahead and watch that. But Bayes' rule is this idea of, there's a couple ways to interpret it, but the way I oftentimes will interpret it is, we start with these initial beliefs, and it gives us a way of taking new information and updating those beliefs. I do recommend, this textbook, at least right now, is not particularly wordy, and he talks a little bit about the sort of philosophical interpretations of some of these things, which I think is good to read. I guess I would call myself a frequentist, but in terms of Bayes' theorem, this idea of updating our beliefs is certainly an important one. So, Bayes' rule. Let's just do an example. I really like the example that they have in the book where they use a polygraph test. One thing I like about this book, it actually points back to some old studies that people have done and uses the data from that to compute, essentially for our probability questions. Okay. So example, I think this is example F out of 1.5 is this question of polygraph test. We'll go through this and then we'll do a slight variation on it and see what happens. So a polygraph test. So this is I think was a study out of the 70s on polygraph tests. And we were told, let's see, from the study that, plus would indicate, right, is a test result that would indicate lying, and then a minus would be a test result that indicates the truth. It almost seems like the plus should be the truth and the minus, anyway. Anyway, the test plus does what it's supposed to, which is, find the liar, and minus indicates truth. Sort of a pessimistic way of looking at the world, I guess. And then T would be someone telling the truth, and L would be someone lying. Right, the event where someone lies. And notice plus complement is equal to minus, and T complement is equal to L, right? You're either telling the truth or you're lying. There's no gray area for us here. And your test result is either a plus or a minus, right? If it's not a plus, it's a minus. If it's not a minus, it's a plus. Okay. And then we're told some conditional probabilities. We're told that if someone is lying, they end up with a plus, meaning the polygraph is indicating lying 88% of the time. That's what we would call a true positive. Think of the polygraph as a screening test, just like you're getting a health checkup and you have some sort of screening test which says, okay, do we need to look at this a little bit further or not? Think of, right, it's not perfect. I'd actually be surprised if it was that high, honestly, but there you go. All right, but 0.88 would be true positive, which would mean that if you're lying, right, if you're a liar, that it would indicate you're telling the truth then 12% of the time, or with a probability of 0.12, right? And that's what we would call a false negative. Additionally, we're told that if you're telling the truth, it would correctly indicate that 86% of the time, with a probability of 0.86, right? So that would be a true negative. You're telling the truth, and it indicates you're telling the truth. And then, of course, given that you're telling the truth, the probability it indicates you're lying, then would be the remainder of it in 0.14. Okay. And that's what I would call it a false positive. I don't think the book uses false positive, false negative, and all of this, but it certainly holds, and since we talked a little bit about some screening tests before, it sort of ties in that same way. Okay, so here's the setup for this problem in the book. Is suppose that a company is going to use this polygraph test on every single one of their potential employees, right? They run them through a screening, and that screening includes probably background check, polygraph tests. We've had enough students go on to work for the government, NSA type things that, they probably call. I've had a number of calls about older students, right, going and working for the government. And sometimes polygraph tests are part of that screening process. And so let's just say that there's a company, there's an organization that uses a polygraph test. Okay? And let's just say that their initial beliefs are that when they're running these tests, the probability someone is telling the truth is 0.9. 99% of the people are just being honest with them, which means that the probability they have a liar in front of them is 0.01. And so the whole goal of this polygraph test, along with the remaining screening process, is to figure out, okay, who's hiding something in their background. And the question would be, is this a worthwhile endeavor to go ahead and do this? Okay. Now, with Bayes' rule, and actually with a lot of these sorts of things, the books almost never talk about tree diagrams, but they're very helpful, especially when we have these multi-step processes, right? Because if we think about this, right, our experiment is we're going to pick someone at random, right? And then we're going to give them their polygraph test, and then that polygraph test is going to say positive or negative, and of course sometimes it'll be a correct positive or an incorrect positive, right? And sometimes it'll be a true negative or a false negative, right? All of that stuff. Right? And so there's an experiment, right? First we pick, let's see, let me keep my notation up, right? Either we have someone in front of us, right? We're going to start the screening process. Is either going to be telling us the truth or is going to be lying. Right? And of course, we said the probability of those happening, the probability I have someone telling the truth in front of me is 0.99, and the probability I have someone lying. This is my prior belief. Do I ever quite know this? No, but I have this belief that this is true. Maybe through background experience, 99% of the time we have a truth teller in front of us, and 1% of the time we have a liar in front of us. Okay. The way we're going to change it from what the book does is we're going to say, well, what if those numbers change? How effective does all of this become in that situation? Okay, so that's the first thing, right? Probably we don't know the answer to this, right? We don't know if we're here or if we're here. That's the whole point of the polygraph, right? If I know there's a liar in front of me, I guess if I'm trying to capture them, right, or I'm trying to get them to say something under the polygraph that I can show that they're lying, I guess I would do that. But typically, I wouldn't know if the person is telling the truth or lying in front of me. Okay. And then I would have the next result, which would be they get a positive result or a negative result, and they get a positive result, and they get a negative result. Okay. And actually, what I like about these tree diagrams is they capture that sort of the essence of this problem, because this one is saying this branch here would be saying, given that someone is telling the truth, what's the probability they end up with a positive? And I can actually read that one off. Oops, truth, positive, this one right here, it would be 0.14. And given someone's telling the truth, what's the probability they end up with a negative that correctly indicates that? That's a 0.86. Given someone's a liar, right? What's the probability that they get a positive, right? It indicates that they're lying. That's a 0.88. And then given they're lying, what's the probability it indicates they're telling the truth? That'd be 0.12. Right? So this branch is telling me the probability my initial belief at least, someone's telling the truth, picked at random, someone's lying, picked at random, and then these branches are, given they're telling the truth, what's the probability of positive? Given they're telling the truth, probability of negative. Given that they're lying, positive. Given that they're lying, probability of negative. And so then the question that is in front of us is, let's see, given that they end up with a test result that indicates that they are lying, what was the question we wanted to ask? What is the probability that they're actually telling the truth? Okay. And notice, that is not one of these things, right? We know sort of those two things swap, right? Given that they're lying, what the probability that they end up with given that they're telling the truth, what's the probability they end up with a positive? Okay? But we don't know the probability that they're positive, given that they're positive, what's the probability that they're telling the truth, right? I can't read it off of this thing. Okay? It's really just saying, okay, if I know that one of these two things ended up being the case, right? What's the probability that it actually came through the truth tellers as opposed to coming through the liars? So I would like to update that belief. And again, there's no particular formula for Bayes' theorem that we need to memorize, right? And we just remember, okay, this is what I want to compute. And the definition in terms of the conditional probability is T intersect plus divided by the probability of plus. Right? That's our definition for conditional probability, that instead of looking at the entire sample space, we've restricted it just to the event in which someone ends up with a plus, right, indicate they're lying, and so it would be T intersect plus divided by plus. Okay. And then I need to figure out this probability for the denominator, this probability for the numerator, and go from there. Now, the denominator, let's take that first. That ties in with this idea of the law of total probability, right? Essentially, it just says, okay, if I want to know what the probability that someone tests or ends up with a positive on their polygraph test, I'm just going to look at all the possible situations in which they could end up with a positive. Okay? And there are just two of them, right? And that's it. There's no third option, right? Either they end up with a positive here, right, by being a truth teller and then lying, and then getting a positive, or being a liar and getting a positive, right? Those are the only two branches. Okay? Or think about it this way. Okay? What's the probability someone ends up with a positive, write it this way, then they're either telling the truth and they get a positive, or they're lying and they get a positive. Right? No third option. Okay? And additionally, right, these two things never overlap with each other, right? You can't be telling the truth and lying at the same time. And that's why I could just add those two probabilities together. Because if you remember back a little bit earlier in this chapter, if I want to add things together, which is what my union does, right? The probability of A union B is the probability of A. Is it the probability of A plus the probability of B? Usually I would do what? In general, I have to subtract off A intersect B. Okay. Now, if there is nothing in the intersection, then that would be 0, and then it would just be, right? So remember, if A intersects B is the empty set, then this gets to go away, and we end up with a nice formula like this. Okay. But that's only when there's no overlap between these two things. Okay. And fortunately for us, right, and this is sort of the underlying thing with the law of total probability is, there is no overlap between the truth teller who ends up with a positive and the liar who ends up with a positive, because you can't be both a truth teller and a liar at the same time. Okay. So that allows me to not need to subtract off the intersection because there is nothing in common between those two things. Okay. And so then it says we can compute that by just looking at all the disjoint cases, all the cases that don't overlap with each other. Should make sure that they can't overlap. And then we can just go ahead and use our multiplication law for conditional probability, which says something like, this is just the probability that someone's telling the truth, multiplied by the probability someone got a positive, given they're telling the truth, right? That's another way to write that one there, right? And then this one would be the probability that they're a liar, right? Times the probability they get a positive, given they're a liar. And that's it. Right? That's, oops, I put two E's in there. That's all that can happen, right? I mean, if there was a third option, then we would say, you know, the probability they blah, right, times the probability they get a positive given blah. But there's no third option in this, right? It's one or the other. And then the nice thing here, and again, I mean, it's a formula, but the book just would lay out this term in the denominator with that in the numerator. But if you think about it in terms of a game tree, really what it's saying, or not a game tree, but a probability tree is, it's the probability that truth, right? It's this value right here times the probability of a positive given the truth. I'm merely just multiplying those two numbers together, right? That 0.99 and the 0.14. Times 0.14. And for the lying and positive, right, this is the multiplication law. It just says, I'm just going to take this number here and multiply it by that, right? Just essentially go out to the end of the branches, figure out which branches I'm interested in, and then I'll just multiply along those branches, and I'll add things up as I go when I'm talking about different branches. 0.01 and 0.88. And that is the denominator there. Okay? So the probability of ending up with a positive is just how many different ways, either through the truth or through the lying. Okay? And then what's the numerator? What number would I use? What value would I use for the numerator? Probability of t and positive. Yeah, I just say, okay, which branches correspond to that, and t and positive is just that one right there. And so I know the probability of that, I just multiply along there, and yeah, it was 0.99 times 0.14. And of course, my denominator is 0.99, 0.14, plus 0.01, 0.88. And so you get a formula that looks something like that, but that's essentially what you're doing. So, you know, you don't have to use these things, but I think pretty much every time I do one of these things, I would set it up that way. Just because then I don't have to, I'm not a big, those who've had me before, I don't like to memorize a lot of things. I like to memorize just enough and then figure everything else out, right? And Bayes' theorem's a good example of that, right? If I just remember the definition of conditional probability, and I just remember, okay, how would I figure this value out? Truth tellers, liars, right? Positives, right? How do I figure that one out? That tree diagram tells me everything I need to calculate without writing down one big formula. Like pretty much every probability book I've ever looked at loves to write that formula down. It doesn't tell us anything, right? Or at least it doesn't tell us much. When it's much nicer just to think it through. Okay. By the way, I gave you guys some time. What value do you get out of here? What's that? 0.94. 0.94. Okay. Right? And now let's think about what that means, right? So this company is just going out there and testing everyone, to test everyone, right? And what it's saying is, I have this new information. This new information is someone ended up with a positive test, right? Somebody had ended up with a test that indicates that they're lying, right? And so, given that they ended up with this positive test, what is the new probability? What's my updated belief? What's my posterior belief in terms of whether or not that person is telling the truth or lying? And the answer is 0.94. Right? It should be, if the test is worth anything, if you give them this test that's supposed to tell whether they're lying, and then they get a positive on it, then it should make it a little less likely that they're telling the truth. Right? And it is a little less likely, but only a little, right? Because what it's saying is that 94% of the time that someone ends up with a positive test here, they could still be telling the truth, or I would expect that to happen, right? Which tells us what? What's the probability they're lying given they had a positive? What would be the remainder of it? By the way, I guess these are approximations, so I should put my little squiggly line equals here, right? 0.06. Right? So if someone ends up with a positive on their polygraph, right, which indicates they're lying, okay, I would expect that the likelihood, right, my update from my initial belief to my updated belief, right, it should increase the probability that they're lying. And this went from 1% to now 6%. That's not wonderful, by the way, right? I mean, what does that really, now just think about this, what does that really tell you about that person now? That they had a polygraph test that indicated they're lying. Doesn't really tell you anything. Not really. I mean, you had a 1 in 100 chance that they were a liar now, and now they have something closer to a 1 in 20 chance, right? So there's a slight, but 1 in 20 means that 19 out of 20 almost are not lying, right? They're telling the truth. So if you actually have a screening test, you would like your screening test to be a little bit more accurate than that, typically. Okay? And so what's the problem? I mean, why did this number end up so small, by the way? Because if you look at it, it gives us true positives 88% of the time, and it gives us true negatives 86% of the time. So, I mean, which seems like it's reasonably accurate. What was the problem in all of this?
What the numbers, those first numbers given don't tell us is the size, the relative size of T and L. So
okay.
With T being so overwhelmingly large, it's kind of like, I don't know, a bag of marbles with 1,000 black and 1 blue or something. It's just still too much, so it outweighs the accuracy.
Yeah, I mean, it's still much more likely that the person in front of us is going to be telling the truth, right? 99% is what we started with. And then the test is still going to indicate 14% of the time, right? 14% of the time we interview those people when we give them this polygraph test that they indicate that they're lying, right? And so it is, this number here just overwhelms that one right there. And you'll see the same thing if you're interested in medical screening tests, the same thing happens, right? When you have these issues, right? These health issues that are really, really uncommon, right? Right. Something that 1 in a million, or well, let's just stick with 1 in a million, right? People have, right? So overwhelmingly, people do not have that. If your screening test isn't perfect, and in particular, if it even occasionally says someone who doesn't have it has it, those numbers are going to overwhelm the number of people who actually have it that test positive to it. Okay? Because you're going to be testing so many more of those people. So oftentimes, you want to have something additional, right, to your screening test, right? You want something additional to your polygraph test. That's why you do background test, right? You just do a background check on people before you do a polygraph test. So let me just change this. So So notice, if we just do this with everyone and it's the first step of our screening process, okay, that's not telling me a whole lot. Okay? But let's just go ahead and change this up just a little bit, and let's just say instead, right, I'm going to change this, and so if someone's going to work for the NSA, we've had a couple people do that. They put the FBI on them to do a background check, right? And they'll call people up and they'll look at someone's background, ask all kinds of questions, right? And let's just say that's the initial step, right? We run a background check on people, and by the time you get through that, let's just say and you give a polygraph test to someone, let's just say there's a 50-50 chance that the person is telling the truth or lying. Okay. Or let's just say, you don't just pick a random person off the street and question them about a murder, right? You actually have collected evidence over time, and so by the time that you're getting ready to, try to get someone under a polygraph test, or they agree to take a polygraph test, that you have a 50-50, you think of, 50-50 chance that person did it or didn't do it, is gonna tell the truth versus lying. Okay? Right? And so how do things change there? Well, the only thing that changes in my tree diagram here is that's now a 0.5 and that one's a 0.5. Okay? But notice, things might change here because now the truth tellers are not necessarily going to overwhelm the liars, right? It's actually just a 50-50 chance on those things. Okay? So if I wanted to compute the probability, what changes in all of this, let's see, this 0.99 becomes a 0.5, this 0.99 becomes a 0.5, everything else is the same, right? It still go through the law of total probability in the same way, I still go through Bayes' theorem in the same way. The only difference is my prior belief, or my sort of initial belief, indicates it's a much more balanced between the likelihood of this person being a truth teller or a liar. Okay. And if we go through all of this, let's see, actually, I use 0.5 because those are actually all cancel out, and I actually get something like 14 or 0.14 over 14 plus 88. I get something like 14 over 102, which should be very close to 0.14. Maybe it's a little less than, maybe 0.136 or 0.137, if I wanted to round it off there. Okay. Which is telling me what now? My updated belief would be the probability that someone's telling the truth, given that they ended up with a positive test, would be approximately 0.137, which means the probability that they're a liar, given that they ended up with a positive test, is the remaining part of it, right? So 1 minus that would be 0.863, right? So about 86% of the time and approximately 14% of the time. Now, does this tell me anything? And the answer is yes, and it probably is much more useful than the other, right? Because remember, our initial problem, we just go out and start testing everyone. The truth tellers end up overwhelming the liars, right? Just because that's an optimistic view of the world, right? That more people are going to tell the truth, right? And my 99% went down to 94%, and my 1% went up to 6%, but that's really not telling me much in terms of, do I trust this person in front of me, or do I not trust this person in front of me? Okay. But in this situation where we did a little legwork, we gathered some evidence, we did some other prior screening to this, so that by the time we get them in front of us and put them on a polygraph machine, I think there's going to be a 50-50 chance that this person is going to be telling the truth versus lying to me. And now what, right? My 50% chance of a truth teller has now decreased to about a 14% chance. Still 1 in 7, right? But better than 1 in 2, right? It's not to say that they are a liar in front of me, but it's much less likely they're a truth teller, and it's much more likely that they're a liar, right? We have about 6 and 7 here, where initially it was about 1 and 2. So, in that sense, we sort of think about Bayes' theorem in this way, right? We had these initial beliefs, and now we have this additional information, a positive test out of them, and given that positive test, we can update the beliefs. It's not going to tell us for certain what's in front of us, but it gives us some updated belief. And it is not uncommon if you start with such a skewed population, that one might overwhelm the other and it actually doesn't help you that much. But if you have something that's much more balanced, it actually can give you some information that can be helpful. Okay. Too bad we don't have a polygraph test, right? We could just go out and start testing people at random. Maybe the psychology department has one of these in there. That's something, a psych experiment. All right, any questions on that and on Bayes' theorem? Okay, right. Bayes' theorem, my recommendation is always just write down the probability you're trying to calculate, right? Write down the definition, because it's always a conditional probability, and then go from there, right? You can calculate the denominator, which usually corresponds to some branches in our tree diagram. Calculate the numerator, which just corresponds usually to just one, maybe a couple, but usually not all of the branches in our tree diagram. And then you calculate those. And again, think of conditional probabilities as given new evidence, what's the probability of something else? Which leads us to the last section of this chapter, which is independence. And there's a couple ways of thinking about this, but the idea of independence is, so if a conditional probability is a way to update the likelihood A occurred, knowing that B also occurred, right? The idea of independence would be, right, A is independent of B if knowing information about B now no longer gives me anything new about A, right? So you could tell me, oh yeah, but by the way, this happened, and you say, well, I don't care because they're independent, right? And then that actually didn't give any additional information, okay? Or, right, if I'm given extra information about A, right, and you say, okay, A occurred, well, what's the probability of B occurring, right? The idea of independence, those two things are independent of each other if that doesn't allow me to upgrade. Whatever my prior belief was, that's what my updated belief is also going to be, okay? Right? So if I tell you, I just flipped this coin, I just flipped this fair coin 100 times and I got heads every single time, okay? And I say, I'm going to flip the coin again, what's the probability I get a heads? 50%. We 1/2, right? If I'm telling you the truth, when you put me on a polygraph, if I'm telling you the truth that it's a fair coin means the probability of heads is 1/2. It doesn't matter if I just flipped it 100 times. I could write a computer program very quickly. It'll take a while for it to run through it, but sooner or later it's going to flip 100 heads in a row. I don't want to do this like in person because it's going to take a long time. But a computer works much faster than we do. Sooner or later, you can flip a coin 100 times. It'll take a long time, probably longer than we have. But sooner or later, it will flip 100 heads in a row if you keep doing it. But it doesn't mean that the next flip is more likely to be heads than tails, right? If it's a fair coin, it would still be 1/2. Okay? So that would be an example of independence. Now, just very quickly here, again, the definition of conditional probability here is probability of A and B divided by the probability of B. Okay. So it's saying the probability of A and B divided by the probability of B is equal to the probability of A, which if I multiply both sides of the equation by the probability of B, then it would say the probability of A and B is equal to the probability of A multiplied by the probability of B. Okay, great. If my events are independent in the sense of this, right, that new information about B does not allow me to change my prior belief about A occurring, right? Gives me no new information. Then one way to write that is the probability of the intersection is equal to the product of the probabilities. Okay. And the same thing down here, right? This would be the probability of B and A divided by the probability of A. And again, if I multiply this one by the probability of A on both sides, I get the probability of the intersection is equal to the product of the probability. Right? I get the same formula. Okay? And so oftentimes, sometimes one of these is given as the definition for independence, or right, we could use this as the definition. So that'll be our definition. We'll just use that one there. A and B are independent if, right, and so we're giving a definition of independent, if I can compute the probability of the intersection of those two things happening by just multiplying the individual probabilities together. Okay. Let's see. We oftentimes, well, we don't always check independence. Certainly, we could sometimes. Oftentimes, we'll assume independence because of the particular type of question that we're trying to answer. Yes?
Is there such a thing as one-way dependence? And dependence, like one thing can be dependent on, like if you know B, it would tell you something about A, but if you know A, it doesn't tell you anything about B.
No, because they both reduce down to the same formula, right? I mean, ultimately, they're both going. It's a symmetric property, right? That if I were to decide to swap B and A around, I'm going to get the exact same formula. Yeah. Now, we will give right, there's an example that we'll talk about in a couple of minutes that if I have three things, when I have three things, everything might be pairwise independent from each other, but when I throw all three of them together, it's not necessarily independent, right? But when I'm just dealing with two things, it's going to be a symmetric property. If A is and B are, if A is independent of B, then B will also be independent of A. Yeah. So an example, right, example that the book gives, and then we'll do a couple of other examples, is suppose I have a deck of 52 cards, and I know people have different experience with decks of cards. People have never, hardly ever played cards, right? But there are 13 of every suit, and there are 4 of every type of number or face value of each card. And so I could look at, I could ask the question, I'm going to draw one card at random from that deck, and I could ask the question, well, what's the probability that I get an ace? So how many aces are in a deck of 52 cards? 4, right? And so the probability of, right, there's 4 outcomes that correspond to ace, and there were 52 things in my sample space. So therefore the probability of drawing an ace is 4 out of 52, or 1 over 13. The probability of drawing a diamond, well, how many diamonds are there in a deck of cards? 13. 13 diamond, 13 clubs, 13 hearts, 13 spades, right? And out of 52 total options, right? Which would be 1 out of 4. And I can say, well, what's the probability I draw an ace and a diamond, right? So really, what's the probability of drawing the ace of diamonds? How many ace of diamonds are in a deck of cards? 1 is a fair deck of cards, right? There's only 1 out of 52. But, here's the question. Is that equal to 1/13 times 1/4, right? Which is the probability of A times the probability of D, and the answer is yes, those two things are the same. Okay. So, the event of drawing an ace, the event of drawing a diamond, those are both independent events. I mean, those are independent events because the probability of A and D is the same as the probability of A times the probability of D. give an example of something that's not independent. So I will roll two 6-sided dice. One red, one green, so we can talk about the order of mattering. It makes it easier. We want to anyway, but right. And so how many things would there be in that sample space? If I roll two 6-sided dice, how many outcomes are possible? 36. Yeah. Okay. Let's make them fair, right? Fair means that every particular side, every particular number on them are equally likely, okay? Right? Because, why do I ask for that? Because then I have 36 equally likely outcomes in my sample space. And I could say, okay, well, the number of ways of getting doubles, I'll put D for doubles. Okay, or I should just ask, what's the probability of rolling doubles? Well, that'd be the number of ways I could roll doubles divided by the number of things in the sample space. How many ways can I roll doubles when I roll two 6-sided dice? 6, right? Because my first one, I have 6 choices for my first one, and then my second one needs to follow suit, right? It needs, that's a card analogy, right? It needs to be the same thing, right? 6 over 36, which is equal to, which is equal to 1/6. And then I could say, well, what's the probability, let's see, so I'll have the event in which they sum to F is the event in which the two dice sum to 4. And that's not an incredibly easy thing. I mean, it's just easier to think about which outcomes correspond to summing to 4, and it would be 1, 3, 2, 2, and 3, 1. Right, would be the sum to 4. Okay. So there would be 3 ways of that occurring divided by 36, right, which would be 1/12. And then I could ask the question like, okay, what is the, well, I should have phrased that. What's the probability of getting doubles and the dice summing to 4? So I just had them written down here. So they would have to be from this list, and then they would also have to be doubles, and how many things are there like that? 1 out of 36. Right. And then I'd ask the question, is that the same thing as 1/6 times 1/12, right? Which would be the probability of D times the probability of F. And this would be 1 over 72, this would be 1 over 36. Those are not equal to each other, so they're not independent. Okay. What does that ultimately mean? It means if you give me extra information like, I just rolled, let's see, I rolled the two 6-sided dice. What's the probability of getting doubles? Well, it's 1/6. Now I'm going to tell you that the sum was 4. What's now the new probability of that I have doubles? Well, there's 3 ways, and how many of them correspond to doubles? 1, right? So there's 1/3. Right? So I could update my initial belief that when you just roll the dice and you don't tell me anything, I say, well, 1 in 6, right? Probably 1/6 that those are doubles. But when you tell me extra information like, you know what, the sum of the dice is 4, and then I now know it's 1/3. Right? So they're not independent. So I can see that lack of independence in 2 ways. I can see it because I can update my probability and get something new, or I can see it because I multiply the probabilities together and it's not equal to the same thing as the intersection of the 2. Okay. This is usually a pretty easy test to do though, where you calculate the intersection of those things. Okay. So, again, with independence, what we often do is something like this, right? We'll just say, okay, I have these independent events. So I'm going to flip a weighted coin, let's just say twice. Let's see which example did I want to do here. Oh, nope, I didn't want to flip a weighted coin. Actually, I'm going to roll the dice. I'm going to roll a 6-sided die. Repeatedly. And let's see. Ace of I will be the event in which I roll a 1, 2, 3, 4, or 5 on roll I. And so I'll do this twice, so if I roll twice, what's the probability of A1 intersect A2? What's the probability I roll a 1 through 5 on the first dice and a 1 through 5 on the second dice? And now we will assume independence. These are independent events. Unless there's some sort of new physics idea that there's a quantum link between one roll of a die and another roll of the die that somehow makes them more likely or less likely from rolls at a distance and time and such to affect each other, right? We'll assume whatever happened on the first roll did not affect what happened on the second roll. Right? That's to say, coin flip, there's a lot of things that we can assume independence. There's a lot of things we can assume independence, but for coin flips and dice rolls and things like that, those are usually pretty good assumptions, right? Which, if I'm assuming independence, says this probability should be the probability I get a 1 through 5 on the first flip multiplied by the probability that I get a 1 through 5 on the second flip. Okay. And what is the probability I get a 1 through 5 on the first flip? 5 out of 6, and the second, 5 out of 6, 5 out of 6 squared, which is 25 over 36. And we could go through and we could count all of those things up, right? There's 36 things in the sample space, and 25 of them would correspond to 1 through 5 for the first dice and 1 through 5 for the second dice. Assuming, again, independence, although we'll have to talk about this for a moment, let's suppose I roll it 3 times. A 2 and a 3. I'd like to be able to say that this would be the probability of A1, probability of A2, probability of A3. And it will be true if they're independent, okay? But there's 2 types of independence here. There's pairwise independence, and there's mutually independent, okay? And this idea of mutually independent will be that if I have multiple things occurring, they're mutually independent if the probability of the intersection of all of them, in this case all 3, is the product of the probabilities. Whereas with this pairwise, 2 things can be independent without sort of as a pair being independent to the third. Okay. And so dice rolls and coin flips and all of those things are also mutually independent, so I can compute the probability in that way, which would be 5/6 cubed. And then I can keep doing it, right? What's the probability that I were to roll a dice 10 times? What's the probability I got numbers 1 through 5 on all 10 times? It would be 10, it'd be 5/6 to the power of 10, right? It'd be repeated multiplication, assuming independence. Okay. But we're running out of time here, and I don't want to go late, so I'll just point out there is an example. I guess we have to talk a little bit more about independence on Wednesday. So on Wednesday, I'll just take questions, if you have questions over homework from the first couple of sections, and then we'll talk a little bit more about independence. But there's an example in the book where, say you flip a coin twice, a fair coin twice, and let H1 be the event of getting heads on the first, H2 event of getting heads on the second, and then E be the event of getting exactly one heads. And you can check that pairwise, each of those three things are independent if you compare any two of them. The probability of the intersection is equal to the product of those probabilities. But when you put all three of them together, you can never have heads on the first, heads on the second, and exactly one heads, right? So that would never happen, but 0 is not equal to 1/2 times 1/2. Right, so when you put all three of them together, they are no longer independent. That would be an example of pairwise independence, but not mutually independent. Okay? So normally when we deal with independence, we have to work a little bit to get pairwise but not mutually independent. That's an example of one such thing. Okay. So we'll talk a little bit more, and again, usually when we deal with independence, it's not just trying to figure out, oh, when are events independent? Oftentimes it's, okay, I know these events are independent, how is it going to help me calculate probabilities? And so we'll look at some of those next. Okay. And I do have homework up on Blackboard already. Intersection.
But in the case of independence, then
Yes, well, so these normally share things down, right? So,
Fortis wins the race.
it has to be a G and like, so what was the example here? It was, F was, they summed to 4, so 1, 3, 2, 2, and 3, 1. And doubles was 1, 1, 2, 2, 3, 3, 4, 1, 5, 6. And this intersection is asking for the things that are in both of them at the same time. In D and in F and in G.
So you add them together and subtract whatever they both have?
No, you just pick the things that, so you're confusing that with union. Yeah, so the probability of the union F, that's the word or.
Yeah.
And that's if it's in this one or in that one.
And then you add them together and subtract whatever they have in common.
And then with the have a common. Yeah, this one is just asking for the things that are in common. And there's just one thing in common.
So the thing that was getting me confused is that, so like, usually you multiply together, it's smaller.
They get super.
Right.
Like things less than 1, but you're saying that you can only do that. So what do you do?
Yeah, but here, they still get smaller.
It's still smaller, but just not as small as.
Oh.
Smaller in a segment, right? So instead of saying, there were 3 out of 36 things here, and there were 6 out of 36 things here, and I can multiply those two numbers to figure out the probability. I actually have to figure it out and say, oh, there's one thing there out of the 36.
Okay, I'm still trying to get this all to make sense, but I think it's getting.
Yeah, independence is they're still getting smaller, but in a very particular, a very full-size way.
I didn't notice that.
That you can do this multiplication. Yeah.
Must have
The thing
been
so
that.
I read that a few times, and I
Yeah.
still, sorry, I have bad grasping.